Hello everyone, my name is Yuxin. I'm an OS architect from Huawei. Today I will present our work about an infrastructure for dynamic library transformation. This research is done with the OLA OS team in Huawei. First, I will discuss dynamic library. Compared to static linked library, dynamic library has a number of advantages. First, dynamic library provides great modularity as it enables complex software to be developed as a collection of libraries instead of a single binary. As a result, it offers better maintainability. Dynamic library can be updated or patched individually without modifying or recompiling the entire application. Thus, the software maintenance cost is greatly reduced. Furthermore, dynamic library can be shared in memory by multiple processes or applications, thus avoid duplication in storage. Last, dynamic library is more friendly to open source usage. There are some open source licenses that requires all statically linked code to also be open sourced. So many production software have to use dynamic library. Given the advantages listed above, dynamic library is popularly used. On one hand, more and more dynamic libraries are shipped by vendors, such as the CUDA toolkit shown in this figure. On the other hand, more and more dynamic libraries are used by applications. It is often that an application relies on from tens to hundreds of dynamic libraries, such as GUI applications and database or storage systems. However, using dynamic library is not free. Let's analyze some performance overhead incurred by dynamic loading. A representative case is ineffective memory management. Each section of each library is individually mapped into the process address space and is likely to be loaded with small pages. Thus, invocation between libraries touch different pages, incurring more TLB miss. We studied this overhead using a macro benchmark that simply invokes 100 libraries. The table depicts the performance of the default glibc loader. Due to loading the libraries with small pages, the benchmark suffers from frequent TLB miss, which further leads to slow and unpredictable execution. We fix the problem by utilizing huge pages, and I will discuss it in detail soon. Another example of performance overhead is relocation. To resolve cross-library function calls, the loader populates the actual address of functions in a lookup table. Thus, a direct function call is converted into indirect jumps. This figure shows a simplified execution flow of relocation. Those relocation mechanisms introduce more instructions and memory access to each of those cross-library function calls. Thus, eliminating those overheads is necessary to achieve optimal performance. And I will talk about our technique to fix it. Now, let me introduce some optimization and techniques we applied for dynamic loading. The first one is called dynamic library concatenation. The purpose of this optimization is to efficiently leverage huge pages in modern hardware to reduce TLB miss. In the high level, this approach collects the same sections from all dynamic libraries and concatenates them one by one to form a big section, and then place the combined section in huge pages. Because all the same sections have the same permissions, they can safely be placed in the same page. Additionally, the combined section is large enough to use huge pages without wasting memory. The figure clearly shows the effect of those techniques. However, this approach has some limitations. By combining sections into a continuous one, we might reduce the entropy of address space layout randomization. To mitigate this impact, we have some options. For example, we can concatenate libraries in random order. Another trade-off is reduced library sharing. Multiple applications cannot share the combined library. In our practice, this trade-off does not impose unacceptable memory overhead, because we can only apply those optimizations to performance-critical applications, while others can still share the library. Next, I discuss the second optimization technique called relocation branch elimination. This technique is pretty intuitive. When loading the library, the loader rewrites the call instruction to replace their target address with the address of library functions, instead of using indirect jumps. As shown in this figure, the performance gain is obvious. We eliminate the extra 2 memory access and 1 instruction branch. As a result, we essentially achieve the performance of static linking on top of dynamic libraries. Despite its simple idea, we have to face some trade-offs as well. First, loading time will increase as we add more functionalities into the loader. For long-running services such as web servers and database, the one-time overhead during the startup is acceptable. The increased binary size is another concern. In general, given the huge disk capacity, the larger binary is not a big deal. If this is an issue, we can download the required information on demand from the remote storage or compress them in the local. In summary, while improving the performance, most optimization has its specific trade-offs and is not a general technique. So how to apply those techniques in a flexible way to satisfy different application requirements is an important design challenge we will discuss in this paper. In addition to above optimization, there is a large body of research focusing on load time technology. However, those research outcomes and features are very hard to integrate it into existing dynamic loader. As a result, the industry and the customer fail to benefit from those advanced techniques. Let me deeply analyze the problem in details. Based on our experience, existing dynamic loader shows a few drawbacks. First, it is hard to develop new features on existing loader. Modifying a loader requires much knowledge about the entire loader logic and introduce ad hoc and intrusive changes. This leads to the second drawback, that the loader is hard to maintain. As we stated before, those customized patch with application-specific optimizations are hard to reuse or integrated into the upstream loader community, causing enormous maintenance cost. Even worse, too many private patches cause the burden on releasing different distributions. For example, to provide the production-specific features, it is painful for the OS department to release different OS or libc distributions with different loaders. Finally, existing loader is hard to use by end customers when they want to combine different features in different application scenarios. So what is the fundamental reason causing those problems? Here, we argue that the root cause is the monolithic design with no interface to allow extensions in current dynamic loader. The loader is designed for a few simple functionalities and acts as a translator. Thus, when adopting new functionalities or features, it cannot be modified in a modular and flexible way. In summary, a new platform for dynamic loading should be designed. In this work, we address those challenges by designing a new infrastructure which has the following design goals. First, it should have extensibility and modularity, so that various functionalities should be organized in a loosely coupled way, instead of a monolithic implementation. Second, flexibility and customizability is desirable, so that the loader can be customized or configured for different trade-offs. In the last, compatibility and transparency is also very important to be a drop-in replacement of the existing loader. Next, let's see the architecture overview of our new infrastructure called iFed. The key idea is to organize the iFed as a pipeline of distinct transformation passes. Each pass only implements some specific features. We also design an in-memory format to describe the state and information about the library and expose the interface to operation passes. A path manager configures and orchestrates the path pipeline. The runnable in-memory format abstracts common information and state in the library, such as relocations and symbols. This is a counterpart to the ELF disk format. Particularly, those formats collect information from all libraries to enable global optimization and coordinate and synchronize the state between different library transformation passes. In this way, the library manipulation is separated from the state maintenance, and a single functionality can be implemented as separated paths. For example, we can easily plug in new function paths, such as binary verification, memory management, and relocation. Now, let's look at the performance evaluation of iFed along with the optimization we introduced above. We evaluate iFed with a large range of applications on different architectures. This figure shows the result on both an ARM physical machine and an Intel virtual machine. The application gets from 4% to 30% performance improvement transparently without any modification to the application itself. We also evaluate iFed in a system-wide scenario, which uses multiple applications to construct a dynamic website. The result illustrates that iFed and its optimization passes offers better throughput, latency, and predictability than the current dynamic loader. Last, we discuss some open questions that worth more research in the future. First, what functionalities should a loader provide? We enhance the loader with some new features, but more functionalities may be also needed in the loader, and it's an open question. Second, we do not argue that our path-based architecture is the only or the best way to design a loader. So designing other new loader infrastructure is still an open research problem. Last, is it reasonable for open source license to rely on the type of linking? This question is beyond the technical perspective, but is valuable to discuss by both industry and academia. In conclusion, we present a path-based infrastructure for extensible, flexible, and modular transformations on dynamic library, and introduce two performance optimization paths. While iFed is not currently public released, Huawei has many fantastic open source communities, covering operating systems, database, and AI framework. Everyone is welcome to contribute and participate in those communities. Thank you all.